Okay, on to section 9.3, and finally some work with planes. In 9.3 on page 510, we're going to talk about, first up, we're going to talk about the intersection or the interaction of two planes, and we're going to talk about three possible cases, three scenarios where we can have two planes interacting or intersecting with one another. We're going to focus solely on the normal components, A, B, and C, and also talk about the importance of the constant D with planes. Okay, but here we go here. So when we have two planes can intersect in a line. Two planes can be distinct from one another, or they could be coincident planes. Okay, and there's the three diagrams and situations here. So there's the first one, intersecting in a line of intersection between two planes being completely parallel with one another, but separate from or distinct from one another. And then the planes being coincident, the two planes being identical to one another, maybe multiples of one another, but certainly coincident, parallel and coincident here. When we consider two planes, we do not ever have a situation where two planes can intersect in a point. Planes don't work that way. Two planes especially don't work that way where there's point intersection. And again, we're going to work through a couple of examples here, and that's it. Now, if you have a hard time visualizing this, again, get two cue cards or two pieces of paper from home and sort of stand with them in three space, in the space that surrounds you, and see if you can model these three situations, right? You certainly can have two planes intersect, right? Just as the diagram shows, just hold these cue cards sort of together there and see that point of intersection. Now, or that line of intersection, I'm sorry. You keep in mind that your two cue cards continue onward, right? The cue card is just a glimpse of the plane, but it goes off in infinite directions on each sides of that cue card. I think you can model two planes being distinct. Just hold those cue cards apart from one another, making sure that they're parallel. And then the third situation, coincident, is easy to model as well too. Just lay the two cue cards on top of one another and see that they'd be coincident here. Okay, so often we're going to be given Cartesian equations of planes, and in this particular case, there's two different Cartesian equations representing our two planes. And notice that we've got three unknowns here, and that sort of poses a bit of a challenge or a problem solving a system of equations when there's only two equations and three unknowns. Okay, a couple of notes here as we try and tackle this issue. Just the things we've talked about here. If planes are parallel and the coefficients A, B, and C are proportional, right? If the planes are coincident, A, B, C, and D are proportional, and a system of equations is compatible if there's at least one solution, and we say it to be incompatible if we can't find a solution. And finally, a system of equations corresponding to the intersection of two planes will either have zero solutions or an infinite number of solutions. Okay, and we might have a situation where we have a single point, or sorry, a line of a solution here. So when we have coincident planes and line intersection, there's infinite number of solutions. And when we have parallel planes, there's zero solutions. And we don't have situations where we have single point intersection, and so a single point intersection equation here that can be solved in a compatible system with a single point here. Okay, so let's look at some examples here. Let's look at this first example here. So in this case, we've got A, B, and C not proportional. We're going to take a look at the normals, and we are going to sort of attack it this way and talk about this equation here. Now, I am going to pause this and go to my my Microsoft Whiteboard and give you some more space to do this particular question. Okay, so here's, let's find the point of intersection, okay, the points, okay, and then we sort of know from this one, okay, it's going to be the line of intersection. I think that sort of gave it away. Okay, the following two planes, we were given Cartesian equations of the two planes here. So for plane 1, okay, I'm going to talk about the normal here, and I'm going to call it normal 1. And this normal is going to be -2, 3, and 1, right? That's just the components. And for plane 2, I'm going to talk about the normal, okay, of 3 and -1 and 2. So that's just these components here, okay? Now, clearly when I write these normals down and look at them, they're not proportional to one another, right? I cannot write this statement. There's no connecting scalar constant here. Okay, so right away when I notice and recognize that there's no common scalar constant that connects these two normals and make them proportional, okay, right away, okay, I know that they're not parallel, and that rules out two cases, right? Okay, it rules out two cases. Now we have three cases, and if I rule out the two parallel plane cases, right away I know that these, okay, planes intersect in a line. We need to sort of understand that. Okay, so regardless of me telling you that in the question, okay, looking at the normals, right, as the very first thing you do, looking at the normals and making, okay, this statement, okay, allows you to conclude that they intersect in a line. Okay, so let's try and find this line of intersection here, and here's how we do this. Okay, so let's take plane 1, and I'm going to write the equation again, and I'm going to decide to eliminate one of the variables here by elementary row operations here. Okay, and I can decide to eliminate any variable I want. Okay, it really doesn't matter. We just have to get the ball rolling here. I'm going to eliminate y. Okay, I think I'm going to eliminate y by, okay, multiplying the second one by 3. Okay, so I'm going to have 9x minus 3y plus 6z. Okay, multiply 3 by, that's a negative 6 and 0. And I'm going to write plane 1 again. Negative 2x plus 3y, okay, plus z plus 6 equals 0. Like I said, I just have to get it started, okay, and I just have to make a decision here. And I thought the easiest one was just to multiply the plane 2 by 3 and add my components now. So when I add my components, okay, I'll have 7x. My y's will eliminate each other, so it'll be 0y. And I have 7z equals 0. Okay, and when I have that, I'm going to rearrange this equation and solve for z. Okay. Now, okay, I just need to pause for a second, and the next step is to take, okay, another, okay, look at the two original equations again, and let's eliminate a different variable. But I want to make sure I still have x, because I want to write, okay, my equation in terms of x again. Okay, so I want to consider the two Cartesian equations again, and this time I'm going to eliminate z and write, okay, y in terms of x. It's always got to be, I've got to find one variable that I'm going to write equations in terms of that single variable here. Okay, so let's take a look at, okay, these two equations again, and I think if I multiply equation 1 by 2, I'll have negative 4x plus 6y plus 2z plus 12 equals 0. Let me box this one here. Okay. Here's this one again here. And I'm going to write plane 2, okay, just down as it was given, 3x minus y plus 2z minus 2 equals 0. And if I want to eliminate z, right, this was eliminate z, this one was eliminate, y. So if I eliminate z, I need to subtract, right? So I'm going to subtract these, okay, and that's going to eliminate, okay, those things. So if I subtract, I'm going to have negative 7z, okay, plus 7y, okay, my z's will disappear, and I'm going to have plus 14 equals 0. And remember, I want to solve for y. So I'm going to bring my 7, negative 7x will become positive 7x minus 14. And I can divide both sides by 7. So it'll give me x minus 2. Okay, so what have I got here? Okay, what have I got here? Okay, I've got y equals, okay, x minus 2, and I've got z equals minus x. So if I introduce the parameter, let x my parameter. Okay. I now have the beginning of my equations. I'm going to write x as 0 plus t. I'm going to write y, okay, as negative 2 plus t. Okay, so this should have been, okay, I'm going to replace this x with a t in here, right? And there's going to be a t up here. I'm going to have z equal, and the original question was z equals negative x, okay, but I'm going to let it be negative t now here. And then another way to write that is just 0 minus t. Okay, so I'm kind of messing this up. Okay, I want to backtrack here and sort of go up to this line here. So I'm going to let, okay, and introduce my parameter here, x equals t. So what happens then, okay, is that y now becomes x minus t, okay, and z now becomes minus t. And I'm going to use these in this equation and develop my parametric equation, okay? So here's my parametric equation. And I can take those together and write that as a vector equation. And that's the vector equation of my line of intersection here. So that'll be, okay, the point 0, negative 2, and 0, 0, negative 2, and 0, plus my parameter times my direction vector here, and that'll be 1, 1, negative 1. And I need setting on my parameter. Okay, there we go. That's the vector equation, okay, of the line of intersection. So that was an important way to do it, okay? And the steps I did, okay, were, okay, start eliminating variables, but make sure you have a common variable so that you have an equation in terms of the same variable. In this case, it was x, right? We start eliminating variables, and we start writing equations in terms of x, and that way that's when we're going to introduce that as a parameter here. That'll be an important example coming up here when we do that. All right, so let's go back to, okay, my next one. There's this parallel and distinct. Okay, so not as hard with this one here. So the parallel and distinct, the first thing I'm going to do, okay, is look at my direction vector here. So my direction vector, or sorry, my normal, okay, for this plane is the 1, negative 1, negative 2. And the normal for plane 2, okay, will be negative 4, 4, and 8. Okay, I also want to state my D values. D1 for plane 1 is 1, and D2, okay, is negative 3 here. Okay, here's what we do. Now, when we look at the normals, we get a feel that they're connected somehow. It looks like if I multiply negative 4 by normal 1, I get normal 2. Okay, now you might see it a different way. You might say normal 1 is determined by taking negative a quarter of normal 2. Okay, so if I factor out a 4 from normal 2, okay, I can get normal 1 here. So if I take a quarter of each of those, I get that. Either way, okay, we're looking for this type of statement here. We're looking for some scalar factor, right? Some scalar factor. If I can write the two normals in terms of some scalar factor here, then I know the normals are parallel, right? I'm just going to confirm that. If I multiply negative 1 by normal 1 by negative 4, I get, yeah, good, okay? So I'll stick with this one. Okay, you can write it however you want. And at this point right here, I can conclude, okay, that the planes are parallel. They're going, okay, in the same direction. Their normal coefficients are, okay, proportions to one another. Okay, now I'm down to two cases now in this case. Now they're either parallel and coincident or parallel and distinct. And to figure that out, okay, we need to focus on the d values. These d values are like intercepts. They tell you where the planes are sort of positioned. And if you like, this plane, if it's negative 3, it's positioned like 3 units down, okay, from sort of the origin point, okay, and this one would be 1 unit above sort of this focal axes or origin points here. The better way to say it is that these two planes are 4 units apart, and I don't know if we can see that, okay, but let me explain that a little bit. Okay, I know they're parallel, and I know this one has a +1 and this one has a -3, so the difference between these two planes is +1 in one direction and 3 units in the other direction. So you have 4 units apart here. So what I'm looking for mathematically, okay, is this. What did I say that my statement was? Okay, but my statement doesn't apply to my D constants, does it? Okay, I can't take D1 and multiply it by that same -4 and get D2. It doesn't work. So when the planes have proportional normals, but that same proportion doesn't apply to my constant value of D, okay, then I say the planes are parallel, okay, and distinct. Okay, that's it. We've narrowed it down to that next case here. All right, now I think you probably know what's coming with this one. When the planes, okay, are intersecting, or the coincident planes, again, we look at the normal coefficients A, B, C, and we look at the constant D, and we look for full proportionality straight across the board with this constant here. Okay, so let's take a look at these two examples. Okay, so for plane 1, I have a normal, and that's 1, -2, and 3, and my D value is +1 here. For plane 2, I have a normal, -3, 6, -9, and my D value, my constant, is -3. Now, can I find connecting ratio here? Okay, yes, I think I can. It looks to me like if I multiply -3 times normal 1, I get normal 2. Does that hold? -3 times 1 is -3. -3 times -2 is 6. -3 times 3 is -9. Yes, it holds. Okay, so let's just check that off. That's correct statement. If you like, you can write it in a different way. A factor of 1, the -1/3 on n2 will give you n1. And then I need to check, okay, if this same proportions, just like I did in the last case, does the same proportion hold for D2? Okay, so is this magic K -3? Is this the one that connects them? Is plane 1, okay, a factor -3 of plane 2 here? Now let's just check it. -3 times 1 is -3. Absolutely, it holds. Okay, so we can do that, and we can really merge these together and say exactly what I said. If I have -3, plane 1 equals plane 2. Okay, that connects them, and this means that these are parallel and coincident planes. Clean this word up here. I don't know what happened right in here. Okay, the word I'm looking for is parallel. Okay, good. And that's clearly, maybe as we have determined that and make those statements, you can probably see that a little bit easier now. Okay, plane 2 is just -3 times plane 1. That's all it is. Okay, the importance then of the normals and the D factors, okay, really go into play here with this. Okay, so let's take a look at 3 cases. I'm going to go to my whiteboard and talk a little bit about how each of these interact with one another. Okay, so we'll all right, let's classify these. Okay, let's classify these, not find any lines of intersection, just classify them strictly. And I'm going to do that by looking at, okay, everything here. Okay, so normal 1 and D1. Okay, I'll let you guys write this down. Okay, D is just a number, it's a constant, right? It always has to be on the left-hand side. Okay, so these Cartesian planes have to be in general form where there's zeros on the right-hand side, and my normal here is 2, -3, and 1. Okay, and this one, my normal 2, use the right notation, please. 4, -6, and 2, and D2. Okay, it's -2. Now, is there a connecting statement here? I'll use blue here. It looks to me like if I double N1, I get N2 here. I just have to check it, right? Okay, double N1, 4, -6, and 2, right? And if I double, okay, D1, get D2. Is that correct? I think so, right? Good. So I can conclude they're parallel and coincident. They're identical planes, just one is double, okay, the other one. Okay, next up, N1, 3, 6, and negative 9. Okay, and D1, negative 3. N2 is 2, 4, negative 6. And D2 is negative 4. This one's not as easy. I think, okay, they are. There's kind of a feel for it. Okay, I think they are. Okay, but here's how we do this. Okay, so in blue, I'm going to say, look, if I double N1 and I triple N2, do I get this connecting statement here? Okay, so if I double this, it'll be 6, okay, 12, and negative 18. And if I triple this one, it'll be 6, 12, and negative 18. So yeah, I do. That works. Now I can rearrange this to write it like this. Okay, so I can divide both sides by 2. And then I have to check that other factor here. Okay, so now I've got parallel planes. I know that. Okay, I want to check my, okay, I'm going to use this factor of k, right? Okay, and check and see if it applies to D1 and D2. Okay, so D1, I'm suggesting that, okay, that's the case here. So if I take D2 and multiply it by 3 halves, okay, so that'd be, okay, negative 4 times 3 is negative 12, divided by 2 is negative 6. It's not the same proportion, is it? It's not the same proportion at all. Okay, so I can say, okay, and that doesn't hold. Okay, and then I can conclude that they're parallel and distinct. Okay, good enough. Let's finish this off here. N1, 1, 2, and 3. D1 is 1, and N2 is 3, 2, and 1, and D2 is 2 here. Okay, clearly I can't make that statement. Okay, just looking at these, there's no connecting. Okay, there's no connecting scalar constant here. Okay, and then right away I can stop and say, okay, these intersect in a line. That's as far as I have to go. I just remember the question was to classify whether they're distinct, coincident, or intersecting. They're one or the other, and there's 3 different cases here. There's really not a lot of work. It's smart work, right? You're looking at normals, you're looking for a connecting scalar constant, and then you're checking to see if that also applies to my D constant here, to see what order these things are in here. Okay, so let's take a look at it. I think that's probably the homework questions. Yep. So that's it for the intersection of 2 planes. Enjoy, and please practice some of these homework questions.